high energy photons or X-rays, which you can do compositional analysis with EDS. But one of the things that happens typically in materials is that electron hole pairs are generated when they recombine, light is emitted, and that light that's stimulated by an electron beam is cathodoluminescence. So it's a really useful technique. It carries the influence of the resolution of the SEM, so it's a much higher resolution technique than you could get with any optical by itself. Now the way we acquire that information is by bolting on a CL detector onto the side of the chamber, as you can see on the schematic here. I have a Monarc from Gatan, our CL product, attached there, but this is generalizable to any CL system. Essentially what happens is a mirror, a parabolic mirror is put into the beam's path, all right, and the mirror has an aperture in it such that the beam can pass through, and then the light that's emitted from the sample is coupled back into our CL tool. So just a few benefits that the Monarc brings to the table. One of them is that it has an extremely high sensitivity, and that comes from the high throughput spectrometer and optics that we've used. It also allows you to collect multiple signals at the same time. So, you know, for some tools or some instruments, you may be able to acquire one signal, then go to another tool and then acquire another signal. In this case, you can acquire CL at the same time as you acquire like a SE, N-lens, or EDS. Anything basically that won't interfere with the mirror being in position, you can acquire at the same time. The Monarc brings with it a whole slew of automated processes that will assist users in finding optimal positions for acquiring the light, for coupling the light back into the system. We'll talk about that in a little while. And then GMS is also coming with some new analytical capabilities, including a nonlinear least squares fitting protocol. So that's pretty nice for us. So this is, again, just a diagram of where the mirror is above the sample, how the electron beam is passing through it, the parabolic mirror is reflecting the light, and assuming that the sample is in the proper position, the light is then collimated back into the system. So then I show this slide to demonstrate that it's of extreme importance in order to have the sample be at the optimal height position in order to efficiently couple the light back into your CL instrument. And so, you know, once you're able to control your CL system, you'll be able to generate really pretty pictures like this one, which is the only reason I show that image. So this is a spectrum image that I've colorized of a bunch of indium gallium nitride core shell pillars. So it's an LED array. All right, so without further ado, I'll just jump in to start using the instrument. So I have a Monarc system mounted onto an SEM, and let's see. Oh. It's currently scanning. And so right now I haven't optimized anything regarding the sample's position. I've just inserted the Monarc's CL collection mirror. It's sitting above the sample. If we zoom out, you can see the aperture in the mirror. So that's what the beam is passing through and striking the sample. Now there's no CL image. This is an SE image, and then I'll activate the CL image. So this is what a typical output looks like in an unfiltered mode. So we're not doing any kind of spectroscopy or optical filtering, anything like that. We just want to get a nice flat field of view in the intensity. Now, like I said, this sample has not been optimized for height. So that's the first thing that I'm going to demonstrate. So then if we acquire a spectrum from this specimen, so I'll just put a spot right on top of this pillar, and we'll view a spectrum. So this is being projected through a spectrometer onto a CCD camera. In this case, we have 670 bins in the wavelength direction. And you can see it's live. There's lots of interesting stuff happening on this sample. But it's not terribly intense, right? So we have a pretty fast acquisition speed on the camera, but we're only getting, you know, there's a pretty decent noise level here. So I'm just going to I'm going to capture this spectrum, and it's going to populate up into a new workspace here, including the 2 images that indicate where we had the beam focused at the time. So now, since I know that we're kind of not in the optimal position, I'm going to raise up the sample, and you're going to see the intensity change. All right, so then I'm just going to raise this up maybe 100 micron. Oh. So I've raised up 100 micron. We've almost certainly lost our SE focus. So I'll go back in and refine that. Not bad. And again, this pillar. And then we'll capture it. Oh, not that. Sorry about that. I pushed serial spectrum capture, so it's going to capture single wavelengths until it quits, and then we'll go back into spectroscopy mode. And then we'll capture this spectrum, which is populated on analytical 2. And we'll just move that over to analytical 1. So this is the first spectrum that we captured. We moved up 100 micron, and now the intensity is something like double. So I could go back and forth trying to optimize or find the maximum level of intensity, or I could sit here and just adjust the stage position until I find that the spectrum maxes out, assuming that the spectrum remains constant and that the beam is not spreading out as a function of height, which are flawed assumptions, but typical of this sort of technique. But in the case of Monarch, we actually have a very powerful protocol here called sample tune. And that's where we actually have a light source inside the CL tool, inside the Monarch, which is going to focus on the sample surface and find the optimal height for me without any more input than focusing the microscope. So what it's doing is it's moving some of the parts into position. So it has to adjust the spectrometer, it has to adjust some of the mirrors, such that we can couple the light back into the PMT sensor. And then we'll adjust the sample's position. It's all automated until we find the optimal height position.
Can you take questions while you're doing this?
Sure. Yeah, I mean, as long as there aren't too many, yeah.
Okay, I wasn't sure what format you were trying to follow with this, but okay. So you're just looking at the light reflected back by the sample? Is that what you're doing here?
That's correct. There's no CL involved right now. So this is a procedure that would really help with like scattered nanoparticles on a silicon substrate, for instance, where there's not a lot of light coming from the sample under the electron beam. You just have scattered emitters. So in this case, it doesn't matter if there's any emission like at all, essentially. It'll find any reflective surface that has, I think it's around 1% reflectivity at around 630 nanometers. So there's a lot of opportunity for it to succeed.
Is 630 nanometers, is that kind of the center of the wavelength range that you capture?
Well, the wavelength range is tunable to a certain degree. The Monarch Pro has 3 gratings inside it. So it has a turret that can freely rotate, and it's automated. You can see in the interface here, I have a wavelength field, so I can just punch in new central wavelengths. Yeah, it's over here. If you look over here in the spectrum, in the spectroscopy technique window, you can see it has these ranges. Those are selected by the gratings. So if I use the 300 grooves per millimeter grating, I get about 400 nanometers of bandwidth across the CCD camera. So it's defined by the grating. So I can change the central wavelength, but not the bandwidth. All right, so this is an example of a successful surface. So you can see the light intensity that coupled back into the system, increased until it reached the maximum and then decreased thereafter. And then we did a fine scan to tune it a little bit further. So now that we're at the optimal height position, we'll refocus the microscope, something like here. And then we'll capture a new spectrum, which is populated in analytical 3. We'll move that over to 1. And so that's the sort of advantage that this automated tuning routine carries with it. You can see in the original spectrum where I just kind of eyeballed it down here, I could have done better, but raising up just 100 microns gave me this red curve, which is a little bit of an improvement. And then letting the Monarch do its tuning on its own, we get a several X increase here. So that's just to demonstrate that now we know, or we have a high confidence that our sample is at or near the optimal focus position beneath the parabolic mirror. So that's key in coupling light back into the system efficiently. And so you can now you can see the field of view is slightly altered from what it was before, but you have a nice flat in light intensity, a nice flat field of view right in the center, so that you can be confident that if you look at a pillar on the left, a pillar on the right, 100 micron this way, whatever, you have comparable intensities. So if you find one bright and one dim, you can quantify that if it's within the flat region. So another thing is to tune the spectrometer in order to both optimize the spectrum that you get, but also to not lose any wavelength resolution. So you want to get your spectral resolution also high. So in order to do that, and again, right now we're not looking at any spectral information, but in order to acquire, say, a spectrum image, you would go to spectrum imaging. We can view the camera. It's moving into position. There we go. So there's a lot of spectral activity, and you want to make sure that you're capturing as much of it as you can in general. But the slit size is controlling. So over here you have the entrance slit size in millimeters, and it's controlling the resolution in wavelength. So if we reduce the slit size, it's obviously going to reduce the amount of light that's able to couple back into the system because we're introducing an aperture, but also it will improve the spectral resolution. So we have a few just easy settings over here, or you could type in freely, or you can put in a slit size as you like. So just as an example, I'll go to a very large slit, so 1 millimeter. And so immediately you see the amount of light that's coupling back into the sensor is increased dramatically because now we're near saturation of the sensor. So that's what this yellow is telling us. So I can reduce the exposure time in order to avoid that. But you don't really get a lot of the fine featured spectral information here. You just see, you know, lines. So then what happens whenever we shrink that slit size? We'll go to 0.1. And again, this is all automated. There are no knobs to turn. There's no manual interface. I don't have to push any buttons or punch anything in. It's all at the GMS interface level. So you can see the spectrum has effectively changed from what it was. It looks a little bit different, but that's a natural thing to happen because we've improved the spectral resolution. So there's less overlap from you know, light that's coupling in at more oblique angles. So it may be off axis, not quite collimated because the entrance slit did not reject it because it was wide. So now that it's narrowed, we get a much more accurate spectrum. And you can narrow it even further, but you'll notice that the counts is always reducing whenever we're lowering the size of the slit. So that was the slit dropping down from, you know, 100 micron to 50 micron. And again, you can see that signal to noise is kind of creeping back. So increasing the exposure time can help, but you don't always have that as an option to increase the exposure time if you want to acquire like a huge spectrum image, for instance. So that's the next thing that we're going to do is we're going to acquire a spectrum image, which is an image made up entirely of spectra.
If I can ask a quick question, just to make sure I understand how you're collecting these spectra. I assume you're scanning the light, so you mentioned a slit, you're scanning the light across the slit and then measuring the intensity as a function of the kind of the offset of the spectrum. Is that what you're doing? I mean, it's not a parallel detection, I guess. You're not capturing all the energy channels all at once.
It is. Right. This is not, it's not serial in any way.
Oh, okay. So then why is there a slit? I guess I don't understand why there's a slit.
To refine, so it's an imaging spectrometer, first of all. So it's not like a typical Cerny Turner that you might be thinking of. But essentially, the more light that you can reject, the more specific the light that comes in becomes. And it also limits field of view. So that's the trade-off. So the amount of light that can efficiently couple back into the system is being restricted by this entrance slit. So as I make the slit smaller, the field of view that you can actually acquire light from is shrunk.
Okay, so it's a way of actually improving your spatial resolution then.
No, it's improving the spectral resolution. The only thing that controls the only two factors in this case that control the spatial resolution are the voltage and
in other words, your probe, right? Your electron probe determines the spatial.
Yeah, so the generation volume.
But you said something about where the light comes from. That's what I'm trying to understand. What do you mean by the field of view? Field of view of what?
So this is my field of view here. When I say field of view, I guess I interchangeably mean the region from where the light is emitted and efficiently collected back into the system. So if I tell you you have, you know, 100 micron field of view, you have an enormous field of view. You can, as far as you can zoom out, that's your field of view. But,
so you're saying light is generated in a larger, much larger area than is being probed by the electron beam. Is that what you're saying?
Negative. So light is being generated by the electron beam. So when the electron beam strikes the sample, light is generated and emitted from that point. or
Mhm.
in and around that point, but not very far.
Okay.
So then if I move my beam, way over here, this is a flat, a nice intensity flat field of view. But if I zoom out, if I mag out, and I'll just do that.
Okay, I think you've now made it clear to me. Because now the place where the light is being generated is much further than from where it was before,
Exactly.
that impacts how it enters the spectrometer, and that's what the slit is affecting, how large an area you can actually acquire spectra from as you're
Precisely.
scanning the probe.
Is it simply just trying to exclude the non-collimated light, the ones that are coming in at different angles? Is that?
Yes.
Okay.
Yeah, that's the primary function of the slit. But you can see there's a tremendous amount of intensity coming from the center here, and not so much as I go further out from center.
So if a ray is coming in at an angle, how does that get misread as a different wavelength?
I don't know that it's misread. I don't know that I would call it that, but it can make it to other channels, basically. Like, so if it's off axis, it won't follow, the appropriate beam path. So it'll be slightly away from that. So there's a numerical aperture that kind of determines the acceptance angles for light entering the system. Yeah, I haven't prepared a lot of that information.
Thank you.
No problem.
This is really cool.
Thank you. Thank you for saying so.
Cool.
So the only other thing that you would need to tune in a CL system, or for certain CL systems, is the position of the mirror. So if I go back to unfiltered, and I mag out, you'll see this nice bright spot, and it should be right in the middle of our field of view. But assuming it's not, you have a manual control, so we can just step around until you agree that she's in the center. I'm pretty happy with that. So again, this is a typical sort of operation on any CL system. So this is all specific to the Monarch, obviously, because I'm using that instrument, but it's generalizable to other CL systems as well. You'll have to do mirror positioning, and you'll have to do sample positioning as well in order to get efficiently coupled light back into your system. But so tuning of the slits is done by looking at the amount of spectral resolution that you effectively see. So if we go back to spectroscopy, and you can see, let me see here. So with a 100 micron slit, we actually have a pretty decent spectral resolution. Monarch is, or GMS is calculating, I have 1.56 nanometer resolution. So it's well above anything I think that we would encounter here. We're not going to find anything of a 1 nanometer bandwidth. But essentially what you would do is you would raise this up until you start to see different spectral activity, and then you would want to lower it down until you kind of stop seeing your peaks shrink. So like this gallium nitride peak is something that you could observe in that process, because it doesn't have any other spectral emission around it. So as you shrink your slit size, you might see it change shape a little. But going from 1 to 0.75 did nothing. See, it doesn't look like much happened there, so we can go even smaller.
Can you say what the inherent wavelength resolution of the spectrometer part is? Like, you know, if you had something that was emitting at exactly whatever, however many nanometers, how wide would the peak look? Just because of the finite resolution of the spectrometer.
Right, the point spread function. It's not very much. It's mostly dependent on all of the reflectors inside the system and the dispersion. Nothing is going to have, like in general, nothing is going to have an infinitely narrow bandwidth. So, I mean,
that's why I'm asking, can you put any kind of rough number on it? You know, even order of magnitude. I mean, do you have, 10 nanometer wavelength resolution, or is it,
well, right now,
1 nanometer?
I can get well below 1 nanometer with the 300 grooves per millimeter grading. I can go even further with my other grading. I have a 1200 grooves per millimeter grading, which is much, much more dispersive. But I can only fit 100 nanometers on the CCD in that case.
Sure, sure. So what you're seeing in that gallium nitride peak, that's the natural width of that peak. It's not limited by the energy or the wavelength of resolution of the spectrum.
I would say that this is the room temperature shape of that peak, yes. Probably a little above because of the beam. Okay. So then something else that you would want to pay attention to is, oh, before I go, that's right, we'll do spectrum imaging. So I'm going to grab a spectrum image, which again is an image that's populated entirely by spectrum. To do that, just throw a 2D array on here. Just a few pillars of interest. And we can set up the camera. So there's lots of little camera settings. You don't really need to bother yourself with that. And then we'll capture. So this is going to take about 4 minutes. It's a 100 by 100 roughly spectrum image. So what it's doing is it's placing the beam and acquiring a spectrum, move the beam, acquire a spectrum. So in this case, we've serialized spatial coordinate. And this is a really useful technique. So then I can pick out a spectrum from anywhere on here. And we can highlight or show what bandwidth is being displayed in the spectrum image itself. So I can move that bandwidth around. So I did one of these earlier so that during the 4 minutes it's acquiring, we can all go look at the data that it would acquire. So this is the same sample. I believe this one is acquired at 5 kV. The one that's in there now is at 10. And once again, you can just see the spectral activity across the sample. There's a lot going on. But you can also cycle through the bandwidth in that spectrum image and change the central wavelength. So there's a lot of activity in these specimens. It's a lot of fun. So then you can generate something that's useful. In some cases, is to generate colorized images. In this case, I'll generate a true color image, which will take the emission spectrum and couple it with the colors of visible light. And so this is generally what that specimen would look like if you could see it while it was being irradiated with the electron beam. Of course, there's a pretty hefty UV component that you wouldn't be able to see, but it would see you. And so that's spectrum imaging. It's a really useful technique. You get spectrum across the surface. You could see lots of interesting activity here and there. Let's see. So I took a pillar on a different sample that's very similar and turned it to a 45-degree angle and acquired a spectrum image on that. And so I mentioned earlier, one of the things that GMS could do in its new capacity was to generate nonlinear least squared fitting. And so that's what I'll demonstrate now. So the information that we get from a typical specimen is coming out in wavelength, right? So it's in the wavelength basis whenever we get it, because the dispersion of a grating is based on lengths, right? So it's X amount of grooves per millimeter. So the information that you're going to get out of it is going to be dispersed by wavelength and not energy. It just so happens that when dealing with band gap emitting materials, the shape of those emissions are in the energy basis and not the wavelength basis. So we would want to transform from the wavelength basis into the energy basis before doing any kind of advanced analysis on this. And so to do that, we have this nifty little button here, and it says convert dispersion units to energy. Let's do that. And so now we have the same spectrum image, only this time in energy. And I can take the picker and drag it over. And now I have two pickers. Oh, the spectrum image just finished. And so now I can roll these around. And you can see that they're both chasing each other, mirroring position both in here and in the survey image. So then I'll go check out the fitting tools. So they're over here in the data analysis panel and data fit. Do nonlinear least squares fitting. And I'll just add a Gaussian peak. I'll let GMS decide where he thinks it should go. He thinks this peak. I'm going to not put a Gaussian on that peak because there's a lot of photonic behavior there. So the closeness and the array orientation of these pillars is such that they interfere with one another and lead to the generation of lots of photonic modes, which if we have time, I'll show that one as well. So I'm going to fit the defect band and the nitride peak. Just integrate a few more pixels here. Make sure that it's seated properly. And then we'll do a fit. So lots of options. You have the option to display them in a new workspace or just populate all of the fit models onto this one. I like to put it in a new workspace. They get cluttery sometimes. You can choose all these sub options for residual or reduced chi-squared. So you can kind of characterize how well your fit went. And so each one of these images represents a parameter that's a variable in the Gaussian fitting. Let's see. So I'm just adjusting the contrast. The default contrast options weren't ideal. So the residual and the fits are spectrum images themselves, meaning that it's not a spectrum, but this stack of information. So there's a three-dimensional stack of information there, and I can look at it. And then we'll do auto layout. So the residual signal is probably the most interesting out of these, other than the fit parameters. And that's because we selected to leave out that that indium gallium nitride interference peak in the fitting algorithm. So we see the gallium nitride fit is over here in fit 2. The spectrum of the defect band peak is over here. And then this is the added spectrum from the gallium nitride peak and the defect band. And you can move that around and you can see how well of a fit it did in each position at every pixel. And more importantly, you can see what's left over. So we can look at this residual signal, and then if it was our desire to try to decompose that further, I think now we're in a much better position to do that because we've removed surrounding peaks and we only have the information of interest remaining. So I'm going to move to, well, I think I don't have time to move to a new specimen, but I do have some data from it that I can demonstrate for you. So the only other thing, the other parameter that you would need to tune as a user is the accelerating voltage. And accelerating voltage is a big deal in dealing with CL because it controls both your resolution and the number of electron hole pairs that you generate. So current and voltage can both generate more pairs, but the voltage is typically controlling the current. So you want to get an idea for your material, what sort of resolution you want to look at. So I've put together a spreadsheet that estimates the electron range as a function of energy, of beam energy. And so then you can punch in different materials and get an estimate, say for 10 kV, what's our electron depth? And then what's the shape of the generation volume? This is the general shape of the generation volume beneath the surface. So that's something that you would want to maybe take into consideration before you set your microscope up at 30 kV and just start blasting away and thinking all your data is pristine. It's marred because your generation volume would be tremendous in that case. At 30 kV, I mean, we're getting at least 2 micron into gallium nitride. So your generation volume is going to be pretty sizable. And that's demonstrable. You can see here. I took a geological sample. It's a polished zircon grain. And you can see at 2 kV, you have very fine resolution, but there are issues with the signal to noise. There's and you can see all of these surface defects that are from the polishing, so the mechanical polishing that was used to prepare that sample. Now, if I go up to 5 kV, you greatly improve the signal to noise. A little bit of loss of resolution, but I think it's workable. And then you're starting to dim out the effects of those surface polishing lines. But if I go even further to 10 kV, once again, it's a bit brighter, but you've lost a little bit in terms of your ability to resolve certain lines. So if you see here, there's a little stripe here. You don't really see it in the 10 kV image. And then if I take it even further to 20 kV, it's very blurry, as you can see. And so each of these images, obviously same sample, and the only thing that changed between them was the voltage of the beam. Well, I think it's a great time to take questions. We've been going for about 45. So if you guys want to help drive it along.
Jonathan, maybe just to get started, one of the questions we had in the chat was, how do the experimental conditions for CL compare to that of EDS? Are they similar in terms of KV, working distance, et cetera?
So typically with EDS, you'd want to go to much higher voltage. So you'd want to go to at least 15 kV so that you have enough remaining energy in the beam so that you can get an EDS signal worth looking at. But yeah, there's a little bit of overlap. So it depends on the sample that you're looking at in either case for CL or EDS. But yeah, there's a bit of overlap there in the 10 to 20 kV regime. So again, it depends on what sort of CL you're looking at. So if you have an infinitely thin sample, for instance, the generation volume argument is flawed. And basically, as well as you can focus the microscope is the size of your spot, because you just penetrate the sample. But in that case, I think, you know, you're losing a lot of signal from the thinness of it. So a lot of those electrons will escape. But yeah, I can, if you guys want to hang out, I can do a side-by-side CL and EDS on a geological specimen.
If you don't mind, another verbal question.
Absolutely.
When you had the gallium nitride sample up there, yeah, you mentioned, or wait, I'm not sure it was the gallium nitride. It's probably the one after that. But anyway, the point is that, yeah, right. You mentioned that some of the signal is coming from like plasmonic effects. So is that actually telling you anything about the sample itself, or more about the geometry of you know, its structure at some level? I'm trying to understand to what degree it's really telling me things inherently about the material itself.
So all the instrument will tell you is what light came out at what wavelength, and then in wavelength and angular mode, you can get up to information about the wavelengths and what directions they were emitted. So you can actually decode or decompose the plasmonic modes or photonic modes that would be in a specimen like this. It's challenging to decompose them though. So from the first specimen I showed you, I have a wavelength angular CL data set. So I'm going to transform that now. So this is what it looks like by itself. So this is the raw data. The y-axis is not something I can explain. The x-axis, oh, it looks like we lost the wavelength information. I can put it in.
So you're just adjusting the calibration, is that what you're doing?
Yeah, the calibration in this file is missing.
Yeah, okay.
So then in the x direction,
And you mentioned the Y dimension. Is this the thing that would get cut off by the slit? As you narrow down the slit, the Y dimension would get cut off?
so in wavelength and angular CL data, actually what we do is we project the light straight back, and then we take the slit and cut the light so that only a small portion of it passes through, but it's still a projected image of the back plane of this parabolic mirror. And then we disperse that. So in one direction, it's decoded, or it's coded angular information. It's not something that can be easily decoded, and it's not constant in either angle, and it's not linear in either angle. So it's challenging to write what this axis is. It's pseudo angle is the best name for it.
Yeah. Fair enough. Thank you. Thank you. Fair enough.
Yeah. So once I remap it, I think it'll speak to you a little bit more, because right now we're in the wavelength basis. But if I remap, this is the back plane of the parabolic mirror. So this is basically what the instrument sees whenever you give it a bunch of light. And this hole is the aperture that the beam would travel down. So right now it's remapping. You can see in the bar on the bottom. I'll just go ahead and ignore the zeros in the image. Put a little gamma on it. Maybe increase the bandwidth. And so as you roll through wavelength, you can see shapes in the light. Let's see, is it clear? Yeah.
Yeah,
So you can see a hexagonal sort of shape that's coming out and changing as a function of wavelength.
and that hexagonal shape is from what?
It's it's coming from a photonic effect in the sample. It was actually, that sample was
Okay.
actually designed to have a photonic behavior, and that's why
I got you.
there are pillars that are so close together in an HCP arrangement.
Okay, great. Thank you. Thank you.
Hi, Jonathan.
Yes.
I had a question about the spectrum imaging. I was curious if GMS will do stage mapping so that you could make a spectrum image of basically a composite of many small areas.
So we don't call it stage mapping, we call it montage.
Okay.
But it's actually a mosaic, so it's neither of those things. So yeah, what it does is it would take an image, but in this case it wouldn't be a spectrum image. It would be some two-dimensional image. It could be unfiltered, or you could pass it through a filter. Like we have several optical filters built into the system. You could do polarization filtering, and then yeah, you can step the stage, 80% of the image size so that there's overlap, and then take another image and you just serialize stage movements. Yeah, that's called montage. It's right here. So in this case, I had it set up to do a 10 by 13 with 20% image overlap between successive images.
That's great. Thank you.
Mm-hmm.
Jonathan, another question we got in the chat is if you could comment on the wavelength detection limit of the system, as well as the spatial resolution that's possible with the CL imaging.
Okay. I'll address spatial resolution first. Spatial resolution is going to be determined again by your beam parameters and the specimen. Those are the two highest barriers to extremely high spatial resolution. So if you can lower your beam condition, but be satisfied that you're going to be very surface sensitive, the more okay with that you are, the smaller you can make the generation volume by going to smaller and smaller voltage. In essence, though, your spatial resolution is effectively limited by the size of the generation volume and the beam. So, if you can focus the beam very, very small, the generation volume is going to be slightly larger than that. And what was the other question?
What's the wavelength bandwidth?
The wavelength limits, yeah. So there are two detectors built into Monarc. And again, this is generalizable to other CL systems. Everybody's going to have their own limitation, but we have an optical window, and that's how we couple light out of the SEM. It's made out of quartz, so it's not very limiting, but if you start to go down into the X-rays, you're going to have trouble getting high efficiency through there. The photomultiplier tube has a wavelength range of something like 180 to 900, something like that. And the CCD is a little bit smaller. It's something like 200 to 800 effectively. The gratings have efficiency that's dictated by their shape. So if you try to go to a very long wavelength with a grating that's been tuned for ultraviolet, you're not going to get any efficiency there either. So it's really a concert of all these different pieces that are contributing to the ultimate spectral capacity. But I've seen as far down as I want to say 280. It's challenging to find specimen that go much further down than that.
Xiaojuan, did that answer your question?
Yeah. So for the spatial resolution, actually, can you give a number?
I think the best spatial resolution I've been able to get from CL is something like 10, 20 nanometers.
Thanks.
That can get better if you have a cryo stage, right?
It can. Again, though, it's kind of determined by your ability to focus the beam spot. So, I mean, if you're really good at focusing the beam spot, then yes, I would agree with that. that even if you go cryo, it'll shrink the generation volume once it meets the sample.
But why does cryo shrink the generation volume? Sorry, it's a very basic question, I know, but.
Because once the carriers are excited, they basically travel around in the specimen before they recombine. They have a little bit of a diffusion length. So
Got it.
they're going to interact with all sorts of things by then. Also, I mean, some specimen like gallium oxide, for instance, won't emit at the band gap at room temperature. So it has a more efficient recombination pathway in the defect band. So when you cool that one, when you cool gallium oxide, you start to change that behavior. And so you can start to see the band-to-band recombination at very low temperatures. So there's an alternate pathway for recombination in that case.
Thank you very much. Thank you.
Sure.
Very clear.
All right. If
I have a question. Sorry.
yes, please.
Hi, Jonathan. It's Carol.
Hey, Carol.
So were you in the showing us in the live demo, and it was doing something, then we went away for a while, and did you ever go back and show us what it was doing for 5 minutes?
Sure. Yeah, this is the 4-minute spectrum image that I acquired at 10 kV from the pillar sample. So we can do a true color on that. You thought I was pulling a fast one, huh?
Curious. So when you're presenting results, you have all of these ways of moving slices around, and is there a way to sort of like, do people usually like capture video or just
So that's one way.
Choose different images that reflect best what they want to show, or how do you?
It's a tricky thing. I mean, it's just like choosing figures for a paper. It's always a challenge because you have to choose something that's both interesting and descriptive. And so CL is really great at generating nice images for public consumption. So other than a true color image, which is kind of useful, we also, so I wrote a script that will generate a color band SI. So this is a spectrum image, or SI. And when I move the slice tool around, like you said, you can see there's different sorts of behaviors in there. And true color is helpful, but it's not, terribly descriptive. So what this does is this just generates 3 images, one red, one green, one blue, at the wavelengths and bandwidths of your choice. So if I wanted to have the blue band centered around the gallium nitride peak, I would just put 365, and then we can look, maybe there's something at 500. There's actually not. Let's put somewhere good.
Oh, there is. Well,
there you go. Let's do 440 is pretty good. And then 560. I guess I used this on the sample before. And then run that script. And so now you have wavelength specific color image that's not a true color image. So these are very, very different. And yeah, so what I would typically do is I would generate like a spectrum, and put, red, green, and blue on a spectrum with a few pickers, because it's a 3-dimensional data set. It's very, very challenging to display to someone, especially in a paper medium. But there is the option to do video. I think was it spectrum image? No. So here you can generate a video. You can say how many frames per second. You can tell it to loop or not. I prefer not to loop. I actually have another script that's really useful for this. The display listener. Let's do red. And so you can generate and save a video in this way.
That's neat. You can do that directly in the software.
Yeah, it's extremely useful.
So these scripts that you've written,
Yes.
are they publicly available?
Some of them, yes. Some of them, I think you would be disappointed by because they're just full of my, my notes in my scripts and stuff. But yeah, we're actually working on posting up on the website an emporium for scripts, specifically for people to come and download and contribute to. So I've added at least the two that I've shown here, and I think a handful of others I submitted. So soon enough on our website, you'll see that.
Okay, great. Yeah, I know that the Digital Micrograph has done that for a long time, but
And
it's very useful for those of us who don't code.
Absolutely.
They're scared of code.
If it's something that you're interested in, I could send you both of these straight away.
Sure.
Okay.
I haven't gotten that far in my application, as you know, but
Right.
always trying to figure out what the capabilities are for our customers, because they don't really know what they can get. So,
Sure.
Yeah.
And if you have questions later that you can't think of now, just email them to me and I'll get back to you.
Great, thanks.
Let's see, color band and display listener.
One thing I'll mention in the meantime is that we've been, as Jonathan mentioned, we've been more actively posting Python scripts and DM scripts on the Gatan website. You can find it under the resources tab, and I'll post the link to that in the chat for the vendor tutorial on the Pathable website.
Thanks, Fernando. Any other questions? All right. Well, like I said, if you think of anything that you'd like to ask later, just shoot me an email. You can find me on the conference website. I hope you've enjoyed the demonstration for cathodoluminescence, and I hope it was educational, and have a great rest of the day.
Thank you. Very, very educational. Very well done.
Thanks,
Thank you.
Jonathan.
Of course.
Well done.
Thank you.
Bye.
Take care.
Thank you.